Voyager 1, a spacecraft operated by NASA, recently utilized a backup radio transmitter that had not been operational since 1981 in order to re-establish a connection with Earth. After decades of silence from this backup system, this spaceship, which is the most remote human-made object from Earth, utilized an ancient transmitter to make a phone call to Earth so that it could communicate with Earth. In this video, we will take a journey through the history of Voyager 1, investigate the significance of this unexpected reconnection, and unearth the crucial lessons that this event bears for the exploration of space in the future. During the month of October in the year 2024, Voyager 1 was confronted with a communication obstacle that effectively tested its durability. On the 16th of October, NASA engineers transmitted an order to activate one of its heaters. This was a normal measure to keep certain instruments warm. Nonetheless, this command triggered the fault prevention system of Voyager 1, which is an automated mechanism meant to defend the spacecraft from probable failures. Voyager's primary X-band radio transmitter, which had served as the spacecraft's major connection to Earth for several decades, was promptly turned off by the system. Voyager's fault protection mechanism took action and immediately switched over to a secondary S-band transmitter, which had not been utilized since 1981. This occurred when the X-band transmitter was rendered inoperable. This transmitter runs at a lower frequency and transmits a weaker signal than the X-band, which presents a problem. Due to the fact that it is located more than 15 billion miles away from Earth, there is a significant amount of time that passes between each order and response because it takes about 23 hours for signals from Voyager to arrive at Earth even under ideal conditions. An immediate answer was provided by the Deep Space Network (DSN) of the National Aeronautics and Space Administration (NASA), which is a worldwide network of powerful radio antennas that are utilized for communication with spacecraft that are located at a great distance. Engineers took great care in tuning the DSN receivers, keeping in mind that transmitting more commands could potentially result in further fault protection responses being triggered. They were able to successfully re-establish contact on October 24, successfully restoring Voyager 1's capacity to restart its scientific mission in interstellar space. This was accomplished after several days of precise adjustments. On September 5, 1977, Voyager 1 embarked on its journey with the intention of investigating the outer planets, which was a task that had never been undertaken by any other spacecraft before. The mission was initially designed to investigate Jupiter and Saturn. Nevertheless, it surpassed all expectations by obtaining groundbreaking data and photos that altered our view of the solar system through its findings. In March of 1979, it made its closest approach to Jupiter, exposing the gas giant's churning storms, complicated atmosphere, and thin rings. This was the first time that humans had a detailed look at Jupiter. The findings did not end there. Voyager 1 was the first spacecraft to observe active volcanoes outside of Earth. It did so by capturing volcanic activity on Io, which is one of Jupiter's moons. Scientific knowledge of volcanic activity was fundamentally altered as a result of this unanticipated discovery, which proved that moons in our solar system might be geologically dynamic features. Following the completion of its mission to Jupiter, Voyager 1 went on to Saturn, where it reached its closest approach in November of 1980. Researchers were able to better understand the structure of Saturn's rings and the gravitational forces that shaped them because of the spacecraft's ability to record exceptional details of Saturn's rings and newly discovered moons. The spacecraft also revealed a faint new ring that scientists refer to as the G-ring. However, the odyssey of Voyager 1 did not come to an end with Saturn. After it had completed its missions to the planets, it continued on a route that would eventually take it outside the solar system. It became the first object created by humans to enter interstellar space when it succeeded in crossing the heliopause in August of 2012. The heliopause is the limit where the Sun's influence ends. By stretching the boundaries of our exploration into the cosmos, this significant feat is one of the most astonishing accomplishments that humanity has ever accomplished. The activation of the backup transmitter on Voyager 1 provides a number of important lessons and insights that can be used for other future space missions. In the first place, it highlights the significance of fault protection methods and redundant systems in the design of spacecraft. The fact that it was able to switch to a backup transmitter after more than 4 decades demonstrates the need for having such redundancies, particularly for missions that are in deep space and are beyond the reach of humans. When it comes to long-duration missions, power management is also quite important. The limited power supply of Voyager 1 has been progressively dwindling, and as a result, NASA engineers have frequently turned down systems that are not required in order to concentrate on equipment that is important for data collection. This method offers helpful ideas for future missions that will take place in low-energy conditions, such as the outer solar system or interstellar space. It places an emphasis on the significance of power conservation in order to maintain operations over an extended period of time. The severe conditions of space, which include cosmic radiation and temperature fluctuations, have the potential to wear out technology over time. In spite of this, the equipment and systems aboard Voyager 1 have continued to operate regularly, delivering crucial data for several decades. Additionally, it has shown that it is capable of operating autonomously in deep space missions. Ever since it passed Saturn, it has been operating primarily independently because of the considerable connection delay. When it comes to missions in remote places where real-time control is not feasible, the capability of this device to identify problems and make corrections without receiving commands from Earth is absolutely essential. In addition, the constant data collection from interstellar space that it has offered has provided scientists with their very first direct measurements of the interstellar medium. These observations have included information on cosmic rays, magnetic fields, and particle densities. This objective has repercussions that extend far beyond the realm of the scientific community. Because of its durability and duration, it has served as a source of inspiration for countless generations of scientists, engineers, and dreamers. It demonstrates that space exploration is not just about collecting data but also about the eagerness and aspiration of humans. Voyager 1 is a metaphor for the human ambition to push past certain restrictions, to explore the unknown, and to go beyond the bounds that are currently known to us. As a result of the legacy that Voyager 1 leaves behind, future generations will continue to be inspired to gaze up at the stars, to wonder, and to seek out the mysteries that lie beyond our solar system. We are grateful that you have chosen to accompany us on this excursion into the fascinating history of Voyager 1. Through its resiliency and adaptation, it serves as a reminder of the boundless opportunities that exist in the realm of space travel as well as the unyielding spirit of discovery. The legacy of Voyager 1 will continue to motivate and direct us as we explore further into the universe, serving as a constant reminder that the quest for knowledge is an endless journey. This is something that we will keep in mind as we work toward future missions.